people are sitting and the screen is in front of them, they are talking to each other.
Right. Okay.
Somebody is counting, they are working, discussing something very important. And they are discussing the next football match.
Yeah.
Honestly. Okay, we are going through the topic of components of traffic system. There are 5 components: road users, vehicles, streets and highways, traffic control devices, and the general environment. We talked about road users, we talked about vehicles, and now we are talking about most important elements of the highway design. We talked about one of them actually, which was this, the side distance. Okay, so this is the most important element of the design of the highway. Okay, and we talked about the side distance which is required for stopping. Okay, there is one more example which we did not cover, which is this one. It is related to the side distance as well. So there is a highway on which the drivers have to slow down from 60 to 40 miles per hour. Why would they slow down? Why would anybody slow down? Obviously, because there is a curve on the highway. Okay, and to make them slow down, now we have to put a warning sign for them. Okay, and the warning sign is visible to the driver, any normal driver, from a distance of 120 feet. Okay, from where did we get this distance? This is from the standards. Okay, when you are going to put a sign on the road, can you put a sign of any size, any height? No, right? Okay, can you use any color? Can the font style be any one which you like? No, right? So there are standards for these things. So when they apply these standards, or whoever came up with these standards, okay, he or they estimated that if you follow these standards, then the driver, a normal driver, should be able to see this sign from a distance of 120. Okay, so since the design of the sign is fixed, so distance is also fixed. Okay, now this is the distance between what? There is a distance between two things, right? Which two things? Vehicle and the sign. Okay, vehicle or the driver and the sign. Okay, where is the driver going? To home, right? So to the curve, right? And what should he do? Reduce the speed. Okay, he is going at which speed? 60. Yeah, he has to slow down to what? 40. First of all, we will calculate how much distance he needs to slow down from 60 to 40. Okay, this is the equation. Initial 60, final 40. Perception reaction time, we take it 2.5 seconds, the normal one. Okay, G, it's not given, will not consider it. Okay, this factor, because they are saying use AASHTO recommended values. Okay, so this is as per AASHTO recommended value. Okay, so now you know everything. Tell me the distance. Okay, you said D is how much? Point something? Huh? 07. 07 is may go from D to F because of 0.07. I don't know. Okay. Now this is the distance between what? Again, distance between two things, right? Which two things? Sine and the driver is how much?
120.
120 feet. This 412 feet is the distance between what?
Raising the speed from 4 to 6.
Who is reducing the speed? The driver. Till when? When he is supposed to have 40? At the curve. So this is the distance between the driver and the curve. Okay, this is the distance between the driver and the curve. The driver start to slow down when he reaches the curve. He should be at 40 miles per hour, and to do this he needs. Okay, distance between the driver and the curve is this much. And between the driver and the curve we have what? The sine. Okay, and how far is the sine from the driver? 120 feet. So now can you tell me how far is the sine from the curve? Right? So I already have take more time. Okay, so I have the driver here and I have the curve here. The driver must travel 412 feet from his position to the curve to go from 60 to 40, right? Between them I have the sine. And how far is the sine? 120. So how far is the sine from the curve? 290. Clear? Okay, this is what they were asking for. And all types of signs, markings, signals, we gave them a name. There's one name for all of them, which is what? Control device, right? So one of the requirements of the control devices was it should give enough time for the driver to react. What reaction are we looking for? Reduction in the speed. How do we give him enough time? By giving him enough side distance. Okay, so the requirement of time is fulfilled with the side distance. Okay. We have discussed earlier stopping side distance, which is a minimum requirement for any road, any highway, any intersection. Okay, so on any intersection you must have enough side distance which you require for safe stopping. Okay, safe stopping, not the other one with the big bang. Okay, the safe stopping. Then there are some locations where we see the driver may not stop. Okay, or even if he stops, he will not be stopping like a normal stopping. Okay, the situation could be much more complex. Okay, and more complex situation, there are higher chances of collision. Okay, there are higher chance of collision, crash, accident, whatever you call. Okay, so there are certain situations which are more complicated. In those situations, there are higher chances of crashes. And those situations, then we should give him more distance to react as well. More distance means more time. Okay, this is what we mean. So what could be these situations which require more distance and more time? Some examples are given here, but the main thing is they have higher complexity. Okay, for example, an intersection or an interchange. Okay, so at intersection you may have pedestrian crossing you, other cars crossing you. You may have to decide whether I should stop or go. Okay, so the situation becomes more complicated. Or an interchange. Interchange is a ramp. Okay, a ramp is called an interchange. A ramp, same thing can happen. A car can come from the other lane, you may have to take an exit and so on and so forth. Other possibility is that the road cross section is changing, which it was doing in the last example, right? What was changing in the last example? Why was the driver slowing down? There was a curve, right? So that is a change in the road, okay, but not so complicated. But for example, you may have other changes which will create some disturbance in traffic. For example, number of lanes are increasing or decreasing. Okay, so when this happens, then people try to go into different lanes. Okay, so that can increase the complexity. Intense demand areas. Intense demand means they call it visual noise, but a more common term is distractions. Too many distractions. Okay, so you have buildings around you, there are lots of cars around you, there's a bicycle lane, there's a pedestrian crosswalk, okay, and there are lots of signs and these things, okay. So they call them visual noise. So there is a lot of information in front of you. Okay, so situation is more complicated because now you have to look at all these things and decide which is more important and which requires some action. So if you are on an open road, there are no buildings around you, there is only one car in front of you, that car stops, you have to only worry about that one car. Okay, but if you are in a congested area and there is car in front of you, there is car on the side, there is a pedestrian, he is just about to cross. Okay, maybe there is another car which is coming from the parking area. Okay, so now you think of it like 3 exams in a day. Okay, so you get it, right? So it's like this. Okay, so those are intense demand areas. So situation becomes more complicated because you have more information. Okay, more information is not good. More information is not always good. People who keep on taking all the notes from the last 10 years, okay, don't do this. Okay, so in all these cases, what is the common thing? What is more here in all of them? Complexity is more. Complexity is more than the driver needs more time. Okay, more complexity, the driver needs more time. So then to give him more time, we have to increase his sight distance. Okay, so in complex situations, having the normal stopping sight distance is not enough because of the complexity of the situation. If you give normal stopping distance, because of more complexity and he needs more time, you are giving him less time with normal sight distance. Okay, so then there are higher chances of collision or crashes. Okay, so to avoid the crashes, then we have to give him more time. Okay, then decision sight distance can be divided, or just animation here. So now you see this is a complex situation because we have 2 ramps here. Okay, so people are going in and coming out within a very small segment. Okay, so there are different lanes here, and you can see it will not play. Obviously, I cannot play. You see it from some other lecture. Okay. Okay, to play it, I have to remove all these things. Anyways, so you can see here it's a complex situation, right? Okay, some vehicles will be going in, some vehicles will be coming out, some vehicles will be trying to go straight, and even in trying to go straight, they have 3 lanes. Okay, so even if somebody is going straight, he may change his lane. Okay, out of these 3, he can go from here or here. Okay, so there is a lot of complexity here. Then in these type of situations, we should have we should give him more time by providing decision sight distance. Decision sight distance can be divided into 2 cases. Okay, the first case is that yes, situation is complex, but eventually he will stop. Okay, so his action is to stop. Okay, but he is not stopping in a normal situation, he is stopping in a more complex situation. Okay, so for stopping, we already have an equation, right? The equation of stopping distance, it will not change because it is coming from speed and deceleration and time and so on. Okay, this is how we calculate the distance for stopping. It will not change. Okay, what will change in the equation? Time. Okay, you will need more time. So you will put a higher value of time because it's a decision or more complex situation. Then we have decision side distance, which is for some other cases, and those other cases may involve changing the lane, speed, direction. Okay, any of the other things. Okay, so he is not stopping. He, like we saw in the example of the sign, the speed sign, he is just doing what? He is just slowing down. He is not stopping. Okay, so that was a complex situation. We will get distance side distance using these equations. Okay, these are the same equation but with different conversion factors. These are just in different units. Okay, same equation. Calculate distance side distance for other actions. We have reaction time and we have maneuver time. Okay, and this is the speed of the driver. Okay, reaction time we know, right? We have discussed it. Perception reaction time. Okay, maneuver time. Maneuver means what? Or changing the lane, or overtaking, or anything, right? Anything. Maneuver is anything which I have mentioned here. Okay, so maneuver is the action. Yeah. So this is the time of action, and this is the time of reaction, right? Reaction happens before the action. See? Okay. So first there is a reaction, there is an action. Okay. And SI means what? Which is speed? Initial speed. Okay. So there is a factor of safety here by using the initial speed. Okay. Because eventually what will happen if you are making a turn, you are going on a curve or doing something like this, you will reduce the speed. Okay. But using the initial speed is the higher one, right? The higher one. If I use higher speed, the distance will also be higher. Okay. So by using initial speed, I am giving him more distance. Okay. I will provide more distance for him. Okay. Using these equations and some assumptions, they have calculated the values. Okay. So the first two columns are for stopping. Okay. So we have used this equation for the first two columns, the equation of stopping distance, without the gradient. The values in the table don't have any gradient. Okay, and the reaction time you can see at the top of the column. So 3 seconds for column A and 9 seconds for column B. Okay, what is the difference between A and B? The type of type of road, type of area. Okay, so you can see rural area 3 seconds, urban area higher, right? Why is higher? Huh? I already explained, right? Why urban? Yes. More complex. Why?
More people.
More people, more objects. Okay, pedestrian and so on. So urban areas have more visual noise. The term they have used. Okay, more distractions. That's why more time. Okay, these three columns are coming from this equation. Okay, so in this equation we have what? Reaction time, maneuver time, and the speed. Right? All these three values are what they have taken, are given in the table. Maneuver time, reaction times, and the speed. So there is no hidden assumption here. Everything is mentioned in the table. If you want to change your values, you have the equations. You can calculate your own values. Clear? Okay. And again, between C, D, and E, the last three columns, what is the difference? The type of fiber, the type of area. Okay. And again, urban areas have the highest reaction. Clear? Okay. Some other types of side distances which we may provide in different circumstances. We have the passing side distance, which is more important for two-lane highways. Why not multi-lane highway? Why only two-lane highway?
We have opposite direction.
So passing happens from the opposite direction. Okay, so that's why it's more critical. Okay, so how to calculate the passing side distance? You have already seen the equations in the highway course. Okay, there's a table given here. Again, if you want to calculate your own values, you go back to those equations and you calculate. Okay, so in this table they have the design speed, the speed of the passed vehicle, the speed of the passing vehicle, and then the passing side distance required. Okay, and if anybody remembers, it was not a single equation. This value doesn't come from one equation. It was, I believe, two equations and one or two assumed values. Anyways, so they are saying if the design speed is 20, then the speed of the passing vehicle is also 20. Okay, so the passing is done at the design speed. Okay, and the difference between the two vehicles is how much? 12. Okay, so 12 miles per hour is around 20 kilometers per hour. Okay, so according to that, passing will happen if the other vehicle is at least 20 kilometers per hour faster than the other one. Okay, the driver will try to increase the speed at least 20 kilometers per hour more or 12 miles per hour more than the other driver before he does the passing. Clear? Okay, then the next one is intersection side distance. Okay, now why intersection side distance is different from the others, all others, whatever we have discussed up to now, intersection side distance is different. Why it is different? Why intersection is different? Why the side distance on the road is different from the side distance on the intersection?
Because in the intersection, you are stopping.
No, because we have thousand more.
More directions. Okay, on the road you are talking about a side distance on the road itself, on the road which you are on. Okay, so if I am going on this road, I am talking about side distance on the same road. For intersection, I am looking where? On the sides, the other roads. Okay, so that's why it's different. Okay, intersection side distance is different because we are talking about the side distance for the car coming from the other side, left side, the right side. Okay, not the car in front of you or the object in front of you. Clear? Okay, we will not do the calculations of intersection side distance. Not, there are no fixed values as well. It's covered in the other course. I will not tell you the name, otherwise you will take it. So there is the course. Okay. Now we have already talked about using the side distance for the design of the control device, right? We were doing it for a speed sign. Okay. Similarly, and I mentioned it in the signal design topic as well, the timing of the yellow light is also calculated using the side distance. Okay. Now the yellow light is basically for a person who sees the signal is yellow and he prepares to stop. The main aim of the yellow is you see the signal is yellow and you prepare to, if you are obviously, if you are far. Okay, so you think the signal is yellow, I cannot cross it, so yellow time should be enough for you to stop safely. Okay, otherwise, not the otherwise. Stop with a bang. No, stop safely. Okay, so this is how we calculate the timing of the yellow. First of all, we should know how much distance the driver requires to stop. Okay, and the yellow time is enough for that driver to make the stop. Okay, this is the theory behind it. Okay, that anybody who sees yellow and he has enough distance should be able to stop at the signal during yellow. Clear? Okay. This is an example. Okay, so we have a road which is approaching towards a signalized intersection. The speed of the road is 40 miles per hour and we are trying to calculate how long the yellow interval should be. Okay, so obviously we will use the equation of, what is this? Equation of what? A stopping distance. Okay, so for this distance the reaction time is 1 second. Okay, for signals the reaction time is 1 second. There's a whole table given in the slides which has reaction time for different situations. Okay, for signal is this 1. Your initial speed is 40 and your final will be how much? 0. Okay, gradient is not given, just ignore it. So give me how much distance this driver would need to stop. Hmm? Point something. Okay, so the yellow signal should be enough for this driver to move at a distance of 212 feet to stop. Okay, so if the signal is yellow, what should the driver do? Huh? Start stopping. Very good. Yes, he should come out and first of all measure the distance, right? Right or wrong?
Right.
You should measure the distance. If it is more than 212 feet, then you would think, okay, I can stop, right?
Right.
Without how you do it, right? Very good. Okay, this distance or anything around it is called as a dilemma zone. Okay, it's called as a dilemma zone. What is a dilemma zone? Anybody who is around this value may think about stopping, or he may think about going. Okay, around this value. Anybody who is less than this obviously will go. He has less distance, right? He will go. Even if he tries to stop, he cannot. It's not possible for him. Anybody who is behind it, he still has a chance. Okay, so we assume that the driver who is exactly in this zone at 212 feet, he will not stop. Okay, he will not stop. He will go, and so he is not stopping means he is not slowing down as well, right? So he will continue at 40 miles per hour. Okay, so he will reach the signal. Signal is still yellow, and then he will cross. And then what will happen? What happens after yellow? Red. Which red? Dark red, huh? Green. Very good. Yes, which red? There's a name, right?
All the traffic light will be red.
Yes. Okay. All red. Okay. So all red is for this guy in the dilemma zone. Okay. All red is for this guy in the dilemma zone who crossed during yellow, and then there we have the all red. Okay. So the yellow time is for this guy who is in the dilemma zone so that he can cross the signal. Now, how much time this driver needs to reach the signal? If he is going at 40 miles per hour, how much time he needs to reach the signal? Tell me, you know the distance. You do the conversion. Speed is in miles per hour, distance in feet. There is no conversion here. You have to do it. Yes. Just divide this 5.3 with the conversion factors in the equation. What happened? You're showing him. I'm asking. Correct? Okay.
Don't you believe me?
Huh?
Trust him.
He doesn't believe himself, and he doesn't believe me. He's asking you. So that's why I'm looking at you. Okay? So before displaying your exam marks, I will ask him, did he deserve this or not? Yes. Okay. So the signal should remain red, the signal should remain green for 3.6 seconds so that the guy in the dilemma zone can still cross the signal, after which it will be all red, and then all red should be enough for him to cross. Okay, anybody who is behind him, okay, he is after the dilemma zone and he has more chances that he will stop. Anybody who is in front of him, he is ahead of the dilemma zone and there are more chances that he will go. Okay, clear? Okay. Another very important characteristic of the highway is its function. Okay, purpose of the highway. Purpose or function of the highway. Any highway or street has two purposes. Okay, one is called as accessibility, the other one is called as mobility. Okay, accessibility is what? This door is an access point. So what do you do from here? Huh? Enter and keep it open. Right? So this is accessibility. Accessibility is the entrance and exits. Okay, so this is one of the purposes. The other one is mobility. Mobility means movement. Okay, mobility means movement, and the movement should be fast. Okay, this is the main purpose. The movement should be fast. So all streets and highways serve these two purposes: accessibility, giving a chance for the road users to enter and exit, and the other one is allowing them to go from one place to the other, movement, okay, at as fast speed as possible. All streets and highways have these two functions, but not at the same level, because these two functions are inversely proportional to each other. Okay, so if you increase accessibility, then the mobility will decrease. Okay, and vice versa. If you increase mobility, then the accessibility has to be less. Clear? Okay, so all streets and highways have these two functions, but at different levels. And according to these levels, we define the classification, the type of the highway. Okay, so these are four main types of highways on the basis of the function. We call it the functional classification. So we have the freeways. Okay, freeways have 100% through service. Through service means without any crossing. Through means straight. Okay, here it means straight without any crossing. So if you remember, we discussed freeways with the uninterrupted flow facilities for calculating level of service and so on. Okay, why uninterrupted? Because they have 100% through service, no crossing. Okay, so you can see this is a freeway. You can see, but this is not a crossing. This is actually a ramp. Okay, so ramp is not considered as a crossing. Okay, but you can see even the ramp is not. It's not like after every 100 meter you have a ramp. Okay, so a freeway has more what? Accessibility or mobility? Mobility. Accessibility is just one point, right? And that point is also not a crossing. It's a ramp. So the highest mobility is for freeways. That means their accessibility is lowest. Okay, and then we have the arterials, the collectors, and the local streets. Okay, so their through service is decreasing, means mobility is decreasing and accessibility is increasing. Okay, so you can see it here as a pattern. Freeway, then we have the arterial connected to the freeway as well as the collector. Collector is then connected to local streets. Okay, you can see the number of access points are increasing. Okay, what about local streets? These are the local streets. Okay, does it have more connections than the collector or less? Huh? More? Where is it? This is a local street, right? How many connections it has? Only one, right? Why we are saying it has more accessibility than collector? Collector has more accessibility, right? Yes, obviously. The slide is wrong. Yes. Because of its length or size. Anything else? It has more accessibility, yes. It has more connections than the collector. Where are those connections? What is this? Huh? Houses, yes. This is road network map. You don't see the houses. Okay. This is what you are doing.
Like the roads for houses.
Houses.
Roads for
Houses are like that. Ready for chopping meat. Okay. Houses which you cannot see here. Okay. So if there are 20 houses, it has 20 connection points then. Okay. This is why a local street has more access points. Okay. Any movement can have 6 stages. Any trip can have 6 stages. Can have, okay? Can have. Not necessarily all 6 of them are there. Okay, but the maximum is 6. The first one is main movement. Main movement takes you from one area to the other area. Okay, that is your main movement. Then we have transition. Transition takes you from one mode to another mode. For example, you are walking. Then you reach the bus stop, you take the bus. Okay, so this bus stop is a transition from walking to the vehicle. Okay, so transition is where you change your mode. Then we have distribution. Distribution is when you enter an area. Okay, when you exit an area, that is distribution. So from distribution you go to the main movement. Okay, or you come out of the main movement. Then you have the collection. Collection takes you into the area, the main road of the area itself. Okay, then we have the access, which is the street where you will find your destination. Okay, the final street where you find your house or something. And then we have the termination. Termination means the end of the trip. Okay, which is university. Yes.
home.
Where else? Home. See. Final destination. Graveyard. Right? What no? What no? Don't believe in death? Final destination, right? Okay. Termination, the doorstep, yes. Okay, so it can have these stages. So for example, this is an old one. I have to change it for Isa Town. So if you are coming from one area to Isa Town, that is your main movement. Then you enter the area, that is your distribution. Okay, if you are on a bus, you get off the bus, that is your transition. Okay, there is a road which is going inside the area, that road is collection. Then you enter inside the gate, obviously in that campus, you enter the gate. Okay, and then the road which is taking you towards the parking, that is the access. Okay, and the termination is this one. Okay, clear? Okay, moving towards the final topic, which is geometric design. Again, as I already mentioned, this is just a revision of what we have already done in the highway course. And you did it with more details here. Huh? Lecture, you mean I will not come on Sunday? Huh? Chapter, yes. I have to be careful with you guys. Yeah, but I'm just trying to make sure that you are at the same level as me. Yes. See, I don't need to teach. Okay. So this is from chapter 27 of the textbook. Okay. This book covers these topics with less details. Okay. And you can see chapter 27. So all the things which we have discussed earlier already discussed in the book as well. That's why I brought this chapter to the end. Otherwise, in the old book, it used to be at the start. Okay. So this chapter is about road geometry. Road geometry has 3 elements. Okay. It has the horizontal element, the vertical element, the cross section. The 3 dimensions, right? Okay. The 3 dimensions. Why are we discussing it here? Because road geometry affects the traffic flow. Road geometry mainly affects the speed. Okay, and then from speed, everything else is affected. Okay, it affects obviously the cross section as well. From where are we getting the method of geometric design? There is a manual which is published by AASHTO. It's called the Policy on Geometric Design of Highways and Streets. Okay, it has been published number of times. You can see now we have the 7th edition, which was published in 2018. According to my knowledge, then did not publish any 8th edition. This one is available online. Okay, so it is followed worldwide. The approach is followed worldwide. Okay, so even if you see the standards or the procedure which they follow in Bahrain for designing of the road, it's the same one which is given by AASHTO, but obviously the numbers, the values are according to Bahrain. Okay, for example, we use more lane widths. Okay, because we have more space, right? See on both sides. Okay. The first element is the horizontal alignment. To see the horizontal alignment or decide the horizontal alignment, you need to look at the area in a plan view. Okay, so plan view means what? You are looking from where? From the top. Okay, so when you are looking on the road or on your plan or your design from the top in the plan view, you will see two things. You will see some straight lines. So there are some parts of the road which are going straight. Okay, they are called tangents. Then at some points the road will change its direction. Okay, so the tangent was going towards north, now it's likely to turn towards east. Okay, and wherever this change is, we need to bring the change with a curve, because vehicles cannot make the change in straight lines in direction. Okay. How do we decide the horizontal alignment? If you have, who was in the last trip? Nobody from here, right? The one which he had on when? On Monday. Anybody from here? No. Anyways, if you go online, you will see the Bahrain map of 2030. What? No? I thought you were going online. Okay. So you will see the Bahrain map of 2030. Okay. And if you look at that map and the highways which they are constructing now, it's according to that map. Okay. So the government decides the future development of the whole area, and the highways are built according to that. They will decide, okay, here we will build or develop a new industrial zone. Here we will have a new residential area, a new commercial area. Okay, and the highways will be designed between these areas. Okay, so the horizontal alignment follows the development plan of the area. Okay, so this is what they were explaining actually in the last the visit which we had to Urban Planning and Development Authority. So they were actually showing that this is our plan and these are the highways we are doing. Okay, the one which you went, the Busattin Link Road, is also part of that plan. Okay, and there are many other highways as well. What other things we need to consider? These are the factors. The first two are coming from the plan. The first two factors are coming from the plan. What are the first two factors? The first factor is how much demand you are expecting on the highway or in the area, and from where it is coming. This is the first factor. Okay, how many people will come to this area and from where? The highway should be connection between these two, right? Where they are coming and from where they are coming. Okay, and the second one is I already mentioned, the development. Okay, sometimes the development is just happening. Business is increasing, people are investing, somebody is coming with another plan. It can happen in this way as well, but again it will go through the government. Okay, so this mainly comes from the government. Then we have the topography. Topography means what? What is topography? Huh? What? Type of land. Type in what sense? Elevations. Okay, elevations of the area. You need to have an idea about it, and for the sake of better design and saving costs and so on. Any natural barriers in the area, river, mountain, sea, woods, what woods? Okay. Forest, okay. 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 Then we have subsurface conditions. Subsurface means what? What is another word for it? There's a course on this. Many of you may have already taken. Foundation. Okay. Foundation, or there's another another name for it, soils. Okay, so these are soil conditions. Then we have the drainage pattern, natural drainage of the area, not the drainage channel. Channel, we will design the channel, but in which direction the water flows naturally, okay, without any channel, okay, or from the surface. Then we have the economic considerations as well, the construction cost, the maintenance cost, the material cost, the land cost, okay, what benefit you will get out of the highway, how much business you will get, how much import, export will happen, and so on and so forth. Then we have the environmental considerations as well. So, more highways means more built up area. So that means less natural area, okay, the forest, the sea and the river and all these things, okay, the desert and so on. So these considerations are also important. Then we have the social considerations. What do the people like and what do they don't like? Okay, think about it yourself. I cannot explain. Okay, and don't ever tell me what you like and you don't like. Okay. Then we have the vertical alignment. Vertical alignment is the profile view. So I'm looking at the highway from where? From the side. Okay. Look at the highway from the side. Again, you will see two parts. One is the gradient of the highway, which will be shown as a straight line, okay, or a bunch of straight lines. And then at some point this gradient will also change. So the point where the gradient changes, we have to connect it with curves, vertical curves. Okay. Gradient we already have discussed a lot about it. We have used it in the calculation as well, and normally it is given as a percentage. Here we try to follow, when we are designing the vertical terrain, we try to follow the topography of the ground, topography of the land, the natural elevation. So land is naturally going upwards, and we design it for an upward gradient. The land is naturally going downward, we design it for a downward gradient. If it is almost level, we will keep our gradient low as well. We cannot make it level. When we say level, it's not actually exactly zero. Okay, there is very small gradient which is required for what? For drainage. Okay, but if the ground is level and you make a 6% slope, then this much material is extra. Okay, so we try to make it as close to the ground to have less extra material. Usually horizontal alignment is done first, and then we look at the vertical design. Horizontal alignment comes from the development plan, right? Okay, from the development plan. Then you start with the vertical alignment. It may happen when you are doing the vertical design, you find that because of the horizontal alignment, I am having too much problem with the vertical alignment. For example, the horizontal alignment showed that the road will go from point A to B, but between point A to B there is a river. Okay, so now you have to build a bridge between them. If you change the horizontal alignment, take it from somewhere else, this bridge cost will be out. Okay, so this can go back to the redesign of the horizontal alignment. Okay, it starts with horizontal alignment, but you may change the horizontal alignment after your vertical alignment design. Okay, so it's a trial and error procedure. Okay, any questions? Clear?